right, good morning, ladies and gentlemen. Hope you guys are doing well. It's Mr. Kenton here. We're continuing our discussion through topic 1 in HL chemistry, and we're looking at stoichiometric relationships. And so we're in our last little section as it pertains to our textbook, and it's going to be looking at how masses and volumes of substances react together, and really going to start to dive into really those stoichiometric problem-solving techniques where we're having to convert between different types of substances. We're going to be moving from masses to masses, or masses to volumes. Maybe it's volumes to volumes. And we're also going to be looking at things like limiting reactants, your percent yield, and we're even going to be looking at gases, gas laws, and some solution components as well as we're moving through this particular section. So as we start here, we're going to start at the basic foundation of how do we do just simple stoichiometric conversions, and then we'll work our way up towards more complicated stuff. So with that, hope you guys are doing well. Hope you're ready for this. I'm excited because it's going to be a lot of math, and I like math. So here we go. Now, as we're looking at this particular topic, what we need to keep in mind is that the mole ratios from a chemical equation can be used to help us calculate the reacting ratios by mass and gas volume. Remember, moles is kind of this universal unit that allows us to make conversions between different substances. Now, as we're going through here and working with these calculations, working through this content, what we should be understanding is that we should be able to make careful observations and obtain evidence for scientific theories that we're using. And so you think about Avogadro's initial hypothesis as it pertains to gas volume in terms of if you had a mole of gas and what quantity, what volume of space it would take up. That's the type of things that we're going to be looking at in this particular topic. Now, again, because IB is just focused on this idea of making sure that we have an international mindset where we're thinking through how does science not only help communicate information here within the United States, but how does science collectively as a whole communicate across different borders and different boundaries. And so you think about this, we talk about units of pressure, for example. You've got the Pascal, which is a Newton per meter squared. But certainly, like if you think about even in the United States, there are lots of other units that are very common and that are used in different countries. You've got things like the atmosphere. You've got millimeters of mercury. You've got torr. You've got bar, pounds per square inch. Right? So you have all these different pressure units that are also still commonly used. Now, the bar, which is 10 to the 5th pascals, is now widely used, and it's a pretty convenient unit because it's close to 1 atmosphere. And we start thinking about the SI unit for volume. The meter cubed is the SI unit for volume. However, we know that the liter is much more commonly used when we start talking about volumes, specifically when we're dealing with liquids. Now, here are some questions to be thinking about in terms of that idea of TOK, of how did we acquire the knowledge that we have, how are we working through that? And so 2 questions for you to consider. Assigning numbers to the masses of the chemical elements has allowed chemistry to develop into a physical science. And just to think through that, why is mathematics so effective in describing the natural world? The second question here, the ideal gas equation can be deduced from a small number of assumptions of ideal behavior. What is the role of reason, perception, intuition, and imagination in the development of scientific models? Again, I don't think you necessarily have to have an answer to these questions when you come to class. We might discuss them during an in-class discussion, but take a look at those questions, think about them, and be thinking through how you would answer them. All right. So as we've introduced this topic, let's dive into kind of the first things that we need to talk about. So when we talk about stoichiometry, should remind us very much of just how we make conversions between different units of substances within a chemical equation, right? And so when you think about a stoichiometry problem, one thing that you have to consider is that you need to know what unit you're given, and you also need to know what unit you're being asked to solve for. Okay, now in these notes, they give you some steps, but they neglect a very important step. In order to do any stoichiometry problem, yes, you need to know the unit that you're given and the unit that you're looking for, but you also need that balanced chemical equation. Without the balanced chemical equation, we won't be able to solve any stoichiometry problem, no matter how smart, no matter how many steps we have. Without that balanced equation, we won't be able to identify the mole ratios so that we can make those conversions between different substances. So just kind of step 0 is have the balanced equation. Step 1 is then going to be, okay, now that we understand what unit I have and where I'm going, then we need to convert what our given unit is into moles, unless we're already in moles, right? So that's pretty straightforward. Because again, once we get to moles, we can then make some conversions to different types of units. Step 2, what you're going to do is once you get into moles of the substance you were given information about, you're going to use the mole ratio from the balanced chemical equation in order to convert into the unknown or new substance that you're trying to solve for. And in your dimensional analysis, the unknown or the substance you are looking for is always going to be on the top, in your setup. And then step 3, you're going to convert to the unit you are looking for using our mole conversion chart, right? So that means we could use Avogadro's number to get to particles, we could use molar mass to get to grams, or we could use the volume conversion in order to move into liters of a gas, right? So let's just take a look at several examples. That's really what we're going to be doing moving forward. So here is a problem that you're given. So it's asking us to go from moles to moles. It says how many moles of water are produced from 6.0 moles of oxygen. All right, so first thing it asks us to do is to label our equation, make sure that we've got our elements balanced and this equation is balanced. And then step 2 is write down the given and multiply by the mole ratio with the unknown on top. And so what I'd like to do now is just kind of walk you through what that setup would look like with this, I think, pretty simple problem, right? So my given in this particular problem comes from, it's going to come right here with our moles of oxygen. Now, I think I'd like to do something other than red. I don't know if that's going to show up very well. So let's go with white. But that's our given. That's our starting point. And so the nice thing here about this question, we're already in moles. So if I come down here, I've got 6.0 moles of O2. In my dimensional analysis, right, I need to go to moles of water, so I'm going to use my mole ratio. In this particular case, I've got 1 mole of oxygen to 2 moles of water. So for every 1 mole of O2 that I have, that's going to produce 2 moles of H2O. Now, because it wants me to go to moles of water, my moles of oxygen are going to cancel, so I'm already set up in the units that I'm looking for. So then I've got 6 times 2, so that means that 6 moles of oxygen is going to produce 12 moles of water. And if you're wondering, I needed 2 significant digits because 6.0 had only 2 significant figures. And so from there, that would give me the number of moles of water for that particular conversion that we needed to do. That should make sense to us. Now, the next couple of slides are going to have a lot of different practice problems for you guys to personally work through. So I think it would be beneficial, like as you're watching this, pause this video, look at each of those problems, solve them, and then once you've solved them, then move on to the next particular section. Okay, so we'll go ahead and go forward. So our mole-to-mole examples, there are 3 right there. Work through each of those on your own, and like I said, pause the video so that you have enough time to work them out, and then you can come back and kind of keep watching through the video. So there's our 3 examples there, and I believe there might be one more set right here, right? So now, using that particular balanced equation, answer those 3 questions as well. So you got 6 problems that you're working on that are going from moles to moles. All right.